Today we're going to be starting Chapter 9, so you need a new tab in your binders and label it Chapter 9. And Chapter 9 is all about quadratic equations, quadratic graphs, and their properties. We've already looked at quadratic equations or quadratic graphs before, and now what we're going to be doing is we're going to be graphing them some more, and we're going to be solving quadratic equations. We're going to talk about quadratic functions. A quadratic function is a function that can be written in the form ax squared plus bx plus c. Now, that there is not a function yet until we set it equal to f of x or y. If this was set equal to 0, it would be considered a quadratic equation. This form is called standard form. Of a quadratic function. And the graph of a quadratic function, when we graph it, makes a parabola. Now, you should be very, very comfortable at this point graphing the basic quadratic function y equals x squared. So what I've done was I set up the table for you already. So we're going to graph the basic quadratic function y equals x squared. Negative 3 squared is 9, negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. So we're going to go ahead and graph the quadratic function. So negative 3, 9, negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. Remember, parabolas have a nice curve at the bottom. They are not done with rulers, so I shouldn't see a point at the bottom. Now, you should be able to graph this function without the graphing calculator, without having to create a table of values each time. So we're going to say be able to graph without the calculator. Now we're going to consider y equals x squared to be our parent function because, again, we're going to be looking at translations with quadratic equations. So that's your basic quadratic function, and now we're going to look at some properties of a quadratic function. First of all, a quadratic function has what's called an axis of symmetry. And an axis of symmetry is the line that divides the parabola into two matching halves. So if I take a look at my graph and I were to cut my parabola directly in half so that each point or each side is symmetric so that I can fold it on top of itself, I would be cutting right along the y-axis. The equation of the y-axis is x equals 0. Now, that's not the axis of symmetry for every parabola. It's just the axis of symmetry for this particular parabola, the parent function. So again, an axis of symmetry is the line that cuts the parabola in half symmetrically. The vertex is the turning point. It's the highest or lowest point of the parabola, and it's where the parabola and the axis of symmetry meet. So we have our vertex, in this case, at the lowest point of the parabola. And in this case, the vertex is the point 0, 0. Now, when we talk about parabolas, we also talk about minimums and maximums. The minimum value is the lowest point on a parabola, and that parabola will open upward. That's a smiling parabola. If the parabola has a maximum, the vertex would be the highest point, and it opens downward. That's a frowning parabola. So a parabola is either going to have a minimum or a maximum. Since in example 1 I have a smiling parabola, that means I have a minimum value. Now, domain and range. Remember from chapter 10, we talked about domain and range. Domain being the x values, how far left and right the parabola will go, and the range, how far up and down the parabola will go. The domain is your left and right. What possible x's can you have? In this case, the parabola goes forever left or right, so we're going to say that the domain of example 1 is all reals. You can also write that as negative infinity to positive infinity. In other words, whatever x value I use in the function, I'm going to get a y value back. I can use any x I want to. However, there's a limitation for the range. The parabola goes forever up, but it doesn't go forever down. The parabola starts at 0 and goes up. So we're going to say the range is y or is greater than or equal to 0. If we want to write that in interval notation, the y's go from 0 to positive infinity. Now, our parabola has what we call symmetric points. And we're going to find f of negative 3 and f of 3 to find out their symmetric points. Remember that this is function notation, which is like an f of x. So I want to know what the value when x is negative 3, what the value of y is. So we're going to say f of negative 3 equals, now we're going to go back to our parabola, and we're going to look when the x value is negative 3, the value of y is 9. So f of negative 3 equals 9. We're also going to find f of 3. So we go back to our parabola, and we look where x is equal to 3, and that's also 9. So f of 3 is equal to 9. Now, if you go back to your parabola again and look at your parabola, when x is negative 3, y is positive 9. And if you notice that when x is positive 3, y is also 9. So those are symmetric points because they are opposite of each other over the line of symmetry. Now, we have increasing and decreasing intervals for our parabola. We talked a little bit about increasing and decreasing intervals in Chapter 10 for our exponential and cubic functions. We're going to do the same for our quadratic functions. The question is, in what interval of the domain is the function increasing? Remember, you read a parabola from left to right, or you're going to read any function from left to right when we're considering increasing and decreasing functions. If you take your pen or your finger or something and you trace along the parabola, and you want to find when this function starts to increase, in other words, when do the y's go up? Well, if we were to continue moving from left to right, we are going down, and we don't start going up until we've reached 0, and after 0, we start increasing. So what we're going to do is we're going to say that the domain is increasing, starting at 0, and going all the way up to infinity. Notice I didn't include 0 because 0 is an actual point. We have to start increasing after 0. Now we saw as we started reading the parabola from left to right that as soon as I started tracing that parabola, I started decreasing. So I decrease all the way from negative infinity up until the point I get to 0. Because at 0 I start turning and I go and I start increasing. So the function is increasing between 0 to infinity, or x is greater than 0, and the function is decreasing when x is less than 0. Now, average rate of change. Average rate of change is, again, something that we talked about in Chapter 10, and I gave you a couple different functions to find average rate of change. Remember, the average rate of change is the change in y over the change in x. We say that's an average rate of change because the parabolas and the other functions that we looked at in Chapter 10 don't have a constant rate of change. Remember that the change in y over the change in x can be rewritten as y2 minus y1 over x2 minus x1. Or we can also write it as f of x2 minus f of x1 over x2 minus x1. Essentially, they're the same formulas, they're just different ways to write them. Pretty much the easiest way to remember average rate of change is to remember the change in y over the change in x. Now, when we look for an average rate of change, we're going to be looking at a specific interval. In other words, the values are going to be at a particular place on the function. So if I want to know the average rate of change going from the interval -1 to 0, I'm going to go back to my function, and I'm going to look from -1 to 0, where the x's go from -1 to 0. So I'm looking at this portion of the function right here. Now remember, we want to find the average rate of change, which is the change in y's over the change in x. So if I look at the change in y goes from 1 to 0, and x's go from -1 to 0. y2 minus y1 over x2 minus x1. 1 minus 0 is 1. -1 minus 0 is -1. So my average rate of change between -1 and 0 is -1. Now, I'm going to do the same thing for 3 different intervals. I'm going to look at the interval 0 to 1, 1 to 2, and 2 to 3. So what I want you to do is I want you to be looking at your graph, and I want you to look at the x's between 0 and 1. And what we'll do is we'll write the work on the second page of the notes. So now this time, because I'm looking for the interval 0 to 1, I'm going to be looking at a different section of the table. In this case, I'm going to have 0 minus 1 over 0 minus 1. The change in y over the change in x. 0 minus 1 is negative 1, 0 minus 1 is negative 1, and negative 1 over negative 1 is positive 1. We go back to the graph to look at the interval going from 1 to 2. So I'm going to change the interval that I'm looking at, and this time I'm going to look at the interval going from 1 to 2. So if I look at the change in y, that's 1 minus 4, and the change in x is 1 minus 2. So the change in y is 1 minus 4, the change in x is 1 minus 2. That gives me negative 3 over negative 1, which is positive 3. And going from the interval from 2 to 3, again, I'm going to look at my table, and I'm going to look at the x's between 2 and 3. And I want the change in y, which would be 4 minus 9, over the change in x, 2 minus 3. So going from the interval 2 to 3, I have 4 minus 9 over 2 minus 3. 4 minus 9 is negative 5. 2 minus 3 is negative 1. So the average rate of change between 2 and 3 on this function is 5. We're going to be doing a lot of work with average rate of change on these functions. You've already done constant rate of change with our linear functions, so now we're going to be focusing on average rate of change, since the rate of change in quadratic functions, exponential functions, cubic functions are not constant. Only linear functions have a constant rate of change. Okay, a quadratic function is a nonlinear function because it doesn't create a straight line, where the rate of change is not constant. It is a symmetric function, meaning we can cut it in half and have a mirror image on each side of that line that I used to cut it in half. And quadratic functions have a minimum or a maximum value. Okay, now if we look at example 2 on the next page, we want to know the coordinates of the vertex of each graph. And I also want to know if it's a minimum or maximum. And I want to know the equation of the axis of symmetry. Because that says I want an equation of the axis of symmetry, there needs to be an equal sign. So let's start off with the vertex. Remember, the vertex is the point that the parabola starts to turn. In A, we have a vertex right at the very top, which is the point 0, 3. Since this parabola is frowning, that means we have a maximum value. Our parabola doesn't go any higher than the point 0, 3. And the axis of symmetry is the line that folds the parabola in half. Since that's the y-axis, our axis of symmetry is x equals 0. In B, taking a look at the vertex is the point where the parabola turns, and that's the point 1, negative 1. This is a smiling parabola, so I have a minimum value. The parabola doesn't go any smaller than that vertex. And the axis of symmetry is the line, again, that cuts the parabola in half. And this is going through the x-axis at 1. So x is equal to 1 is the equation for the axis of symmetry. These are very, very important properties of quadratics that you need to be aware of. You need to be able to state and label the vertex, state and label the axis of symmetry, and be able to tell me if it's a minimum or maximum value. Okay, in number 3, I want you to graph the function y equals negative 1/2 x squared plus 4x plus 1. I want you to make a table of values, so you're going to be going to your graphing calculator. I want you to tell me the domain, range, vertex, axis of symmetry, and if it's a minimum or maximum. So at this point, what I want you to do is I want you to do this work independently. We're going to pause the video. When I come back to, when we come back to the video, I will have the question completed. So I want you to spend the next few minutes completing example 3, and then when you come back to the video, I will have the question complete. Okay, notice I completed my table of values, and I graphed my parabola. I have my axes labeled, and I have the parabola labeled. Now, your domain. Remember, the domain is how far left and right the function can go. Since this parabola goes forever to the left and forever to the right, our domain is going to be all reals. You could also write that as the parabola goes from negative infinity to infinity. The range is how high up and down the parabola goes. If you look at this parabola has a maximum point of 9, and it goes forever down. So that means that the y's have to be less than or equal to 9. If we wanted to write that in interval notation, we have negative infinity up to positive 9, and we can include positive 9. Remember, the vertex is the point that the parabola begins to turn. So our vertex is the very top of the parabola in this case. We can also find the vertex in the table because that's the point of symmetry. That's where the parabola starts to repeat itself. The axis of symmetry is the line that cuts the parabola in half. So if I were to cut this parabola in half, I'd have a line cutting through the x-axis at positive 4. So my axis of symmetry is x equals 4. And this parabola has a maximum value because it's a frowning parabola. It doesn't go any higher than the point 49. Okay, let's take a look at the final example. Number 4 is a word problem. An acorn drops from a tree branch 20 feet above the ground. The function h equals negative 16 t squared plus 20 gives the height, h, of an acorn in feet after t seconds. So t is my number of seconds. What is the graph of the quadratic function, and about what time does the acorn hit the ground? Okay, so what I want you to do again is I want you to graph this function. This time, instead of x's and y's, I'm going to have h's and t's. Now remember, t is time, and time can't be negative. So when we graph this parabola, we're not going to have negative time. And since h is height, we're not going to have any negative heights either. That means when you graph this parabola, your parabola should only be in the first quadrant. So I want you to pause the video. I want you to graph the function in the first quadrant only. When you get your table of values, you're going to have to only use a couple of those values, and then we'll have to supplement them with some other values. So go ahead and pause the video and see if you can get a graph of this parabola. Okay, now what I've done is I've gotten my values from the graphing calculator, and I have the point 0, 20, and then I have the point 1, 4. And those are the only values that I can get from the graphing calculator without the negative values showing up. So my parabola, I'm only going to see a little portion of that parabola. What I'd really like to have, though, is a few more values in order to create a better looking parabola. So what I'm going to do is I'm going to find the point right in between 0 and 1, which is 1/2. Now, of course, I can't get that value from the graphing calculator. I actually have to substitute it in. So I'm going to say that h equals negative 16 t squared plus 20. And I want to know what h is when t is 0.5. Now, if you do all that math in your graphing calculator, you're going to get h is equal to 16. So when the t is 0.5, the h value is going to be 16. So you can see I'm going to have a slight curve like that. Clearly, we're not going to see the entire parabola because we can only be in the first quadrant. So that's a graph of the function. The next question is, at what time does the acorn hit the ground? So notice we're just beyond the value of 1 here. So we're going to have a time that's a little bit greater than 1. We just have to figure out what it is. Now, the acorn hitting the ground means the height is equal to 0, because if the acorn's on the ground, it doesn't have a height. So what I'm going to do is I'm going to substitute a 0 into my function for height, and I'm going to solve this function for for t. So I'm going to subtract 20 from both sides, and I get negative 20 equals negative 16t squared. Now I want to get the t by itself, so I'm going to divide both sides by negative 16. And I get 1.25 is equal to t squared. Now I need to solve this for t, not for t squared. So remember, if we want to get rid of a squared term, we have to take the square root of both sides. So putting the square root of 1.25 in your calculator, you're going to get approximately 1.12. So the acorn will hit the ground at approximately 1.12 seconds. We can also find this value on the graphing calculator, and what I will do is I will show you that tomorrow when we go over some more properties of a quadratic function.